Here's Precalc. It's your lecture for 10.2.2. It's how can I use parametric equations? So it has some applications for parametric equations. This first one, I'm not going to do it, but I'm going to show you a video. It's called Shoot and Drop, and it's a YouTube video where they show when they shoot, if you shoot a ball out, like, and it goes out like this, and it drops down, and you also at the very same time just let a ball drop, they'll both hit the ground at the same time, even though this one looks like it, traveled in a in a horizontal motion. So there'll be a little video clip that'll be with all their, well, I'll send it to your Google Classroom. So I'm going to skip this because you're going to watch the video clip of that. It's only like 1 or 2 minutes long. And then this one here, we're going to do this one together, but it has a Desmos, it shows a little seagull, and it has little sliders, and you can show, this one's about a seagull that drops a shell, and so I'll just give you a link to that. So let's go ahead and just do 10-119. It says, while sitting on a pole 256 feet above the ground on a windy day, a gull drops an oyster shell. The wind is blowing the shell sideways, but as seen in the coin demonstration and in the shoot and drop with the ball, it's going to be a ball that gets dropped and a ball that gets shot, and you'll see that the height's only affected by gravity. Like, it doesn't matter if there's some kind of horizontal motion, it'll still hit the ground the same as if it were just dropped straight down. So it says, suppose the wind is blowing the shell sideways at 22 feet per second. So the shell's position in relationship to the pole at any time t seconds is x of t equals 22t. Of course, the shell falls faster and faster as time increases. Ignoring air resistance as the shell falls, the height, y, in feet, of the shell at time t in seconds is given by y of t equals negative 16t squared plus 256. So you'll always see that negative 16t squared, that's acceleration due to gravity. That's why you've probably seen that many times on word problems, like where usually when you're studying parabolas and stuff, you'll see that. It's like when an object gets thrown and it falls. It has to do with gravity. So here we go. Letter A says, make and complete a table with 3 columns as shown below for t in between 0 and 4. Well, I have a little resource page for that. So this right here, all this is the same exact thing as this, which, oh, you can't see very well. Maybe you can see it now. So this is a parametric equation, kind of like we were doing this before. If you remember, last time we had the rabbit and the fox, and so I did a video on this, and maybe you've had some problems. This is the same kind of deal. I'm going to plug the time in. There's an X, an X part that controls the horizontal motion, and then there's a Y part that controls the vertical motion. So you plug the 0 in, and then you plug the 0 into this one, and you get your Y. So these are all ordered pairs, and I checked them off because I completed this table. Just hopefully you can see that it's all I'm doing is plugging, like plug a 4 in there. 22 times 4 is 88, and then plug the 4 in here. Oh, this ended up zeroing out because 4 squared is 16, and 16 times 16 is 256, and negative 256 plus 256 is 0. But anyway, we get all these, and then they make ordered pairs, and then here's a graph of the ordered pairs, and then it's going to ask us some questions like, what does it look like? Like, I think it looks like a part of a parabola or something. You're supposed to say that it looks like half of an upside down parabola. when did the shell hit the ground, and how do you know and confirm your answer algebraically? Well, when its height was 0, it must have hit the ground. So when was that? That was at 4 seconds. And I don't know if I did that algebraically, but when y of t equals 0. So yeah, so what you could do to algebraically show this is set this equal to 0. So you would subtract 256 from both sides, and then you would could divide both sides by -16, and then take the square root. And I see now, like, I can do it kind of in my head. I would get 4 if I did that. So that's how you algebraically would do that. And then letter D says, determine how far the shell has traveled horizontally when it hits the ground. Well, I like using my table. I see that it hit the ground here, so 88 feet. And you can use your graph too. Okay, so, and then letter E says, how would the parametric equations be different if the wind were blowing at a rate of 10 feet per second or 40 feet per second? Well, we found out with the shoot and drop little video clip of the ball falling and the ball kind of going in an arc or going straight down, we found out that the vertical motion is not affected by the horizontal motion. So your vertical motion happens with the y, and that's going to remain the same. And then x of t would be 10t or 40t, because on here I was 22t. So, and that's because, wasn't that because the wind was blowing 22 feet per second? So you would, if the wind were blowing a different, like not 22, then you would, however many feet per second is blowing, that's what you would put in for the horizontal movement. And then on letter F, it says on the graph, but using different colors. I didn't use colors. Plot the graphs of the motion of the shell if the wind is blowing 40 feet per second, 10 feet per second, 5 feet per second, and not blowing at all. And so one of them looks just like, this is the one that we already did, that was, the wind was blowing 22 feet per second. And here's 0 feet per second, 5 feet per second, 10 feet per second. Here's the one that I had graphed on that other paper, 22 feet per second, 40 feet per second. Okay. So in each case, the shell is still hitting the ground after 4 seconds. So I don't know if you already knew that because of your physics classes or whatever. We're gonna do one more problem, and I'm gonna make a second video for that. It'll be part 2.